Imagine standing in an open field and throwing a ball straight ahead with all your strength. You expect it to travel exactly in the direction you launched it, but now imagine something strange happens. The ball still moves forward, yet very slightly, almost imperceptibly, it drifts sideways. Not enough to miss your target by much, but enough that precise instruments could measure it. Naturally, you would want to know why. Something must be pushing it. Something small, something subtle, but something real. This is essentially the mystery scientists are facing right now with an interstellar object known as 3I, Atlas. The object is drifting sideways through space, not dramatically, and not enough to change its journey through the solar system in any significant way. After an entire month, the sideways shift amounts to roughly half the radius of Earth's moon. On a cosmic scale, that distance is almost nothing. But the direction of the push does not match what scientists expect, and that is where the real puzzle begins. To understand why this matters, we have to step back and examine a simple question. What forces actually move objects in space? Most people assume the answer is gravity, and in most situations, that assumption is correct. Gravity dominates the motion of planets, moons, asteroids, and spacecraft. If you know the position and velocity of an object at one moment, you can apply the laws of motion described by Isaac Newton, along with corrections from Albert Einstein, and you can predict where that object will be far into the future with remarkable accuracy. For a lifeless rock drifting through space, gravity is almost the entire story. But comets are different. Comets are not inert stones. They are active objects made of ice, dust, and frozen gases. As they move closer to the sun, sunlight heats their surfaces. Ice turns directly into gas through a process called sublimation. When that gas escapes from the comet's surface, it shoots outward into space. And here we encounter one of the most basic principles in physics. Every action has an equal and opposite reaction. When gas erupts in one direction, it pushes the comet's nucleus in the opposite direction. This tiny push is known as non-gravitational acceleration. Scientists have been measuring this effect for decades. Every active comet in our solar system experiences it. The effect is subtle but detectable. Astronomers compare the comet's actual position with where it should be if gravity were the only force acting on it. If the comet appears slightly ahead, slightly behind, or slightly off to the side of its predicted position, then something besides gravity must be pushing it. Over months of careful observations, these deviations accumulate and reveal both the strength and direction of the extra force. Back in 1973, three researchers, Brian Marsden, Zdeněk Štěpánek, and Donald Yeomans, developed the mathematical framework scientists still use today to describe these forces. They divided non-gravitational acceleration into three components. The first, called A1, points directly away from or toward the Sunday. The second, A2, runs along the comet's orbital path, essentially pushing it forward or backward along its trajectory. The third, A3, points above or below the plane of the comet's orbit. These three numbers, A1, A2, and A3, tell scientists exactly how a comet is being pushed by its own escaping gases. To understand the debate surrounding 3I, Atlas, we need to know what normally happens. In a typical comet, sunlight heats the side facing the Sunday. That side releases the most gas. If the comet were perfectly spherical and evenly covered with ice, gas would escape across the entire sun-facing hemisphere. The combined effect of all those jets would push the comet almost directly away from the Sunday. That means the radial component, A1, should be the largest. The transverse component, A2, which pushes sideways along the orbit, should be much smaller. Real comets are more complicated than this simple picture. They rotate. Their surfaces are patchy. Some areas contain exposed ice that releases gas vigorously, while other regions are covered in dust that blocks activity. These active regions can create jets that shoot gas in particular directions. But even with all this complexity, the general pattern still holds. The main push tends to point away from the sun because solar heating is the driving force. That expectation is exactly what the official analysis from NASA initially suggested. According to the orbital model published in the database maintained by the Jet Propulsion Laboratory, the radial acceleration, A1 for 3I Atlas, is roughly 5 times larger than the transverse component, A2. In other words, the comet appears to be behaving like a normal comet. Gas escapes primarily from the sunlit side, pushing the object outward away from the Sunday, but not everyone agrees with that conclusion. A new scientific study released in early March 2026 proposes something very different. The research, led by astronomers including Federico Spada and Malgorzata Krolakowska, suggests that the sideways force may actually be just as strong as the outward push. If that result is correct, then 3I, Atlas is not simply being pushed away from the Sunday, it is also being pushed sideways through space. Before we dive into that disagreement, we need to understand why measuring these forces is so difficult in the first place. Detecting non-gravitational acceleration requires extremely precise measurements of a comet's position in the sky. Astronomers perform this work using a technique called astrometry, which determines an object's location in terms of right ascension and declination against a background of reference stars. Modern telescopes can measure positions with astonishing accuracy, often to fractions of an arcsecond. Yet, the force acting on 3I, Atlas, is incredibly small. Its total acceleration is only about 1 micrometer per second squared at Earth's distance from the Sunday. Over an entire month, that tiny push shifts the object by only half the radius of the Moon relative to where gravity alone would place it. Compared with the enormous distance between Earth and the Sun, that shift is smaller by a factor of about 200,000. To detect such a faint signal, scientists must combine many measurements collected over many months. Each observation carries its own uncertainty. Atmospheric distortion, telescope calibration errors, and the precise positions of reference stars all introduce tiny inaccuracies. Individually, these errors are small, but together they complicate the analysis. And in the case of 3I, Atlas, there is another complication. In October 2025, the object passed behind the Sun from Earth's perspective. During this period, known as solar conjunction, telescopes on Earth could not observe it. That created a gap in the data at the worst possible moment, exactly when the comet was closest to the Sun and its outgassing activity was at its strongest. Scientists therefore had to model what happened during that unseen interval. Different assumptions about that hidden period lead to different answers about the sideways acceleration. That is why the transverse component, A2, remains the most uncertain piece of the puzzle. And that uncertainty is exactly where the disagreement between NASA's model and the new study begins. In the next part, we will look closely at how each team analyzed the data, why their conclusions diverge, and what their results reveal about the mysterious sideways push acting on 3I, Atlas. If you're fascinated by the idea that a tiny force can reveal massive secrets about an object traveling between the stars, stay with me, because in the next part, we'll uncover how two competing analyses of the same comet are leading scientists toward very different conclusions, and why the answer could change the way we understand interstellar visitors to our solar system. The disagreement between two scientific teams studying 3I, Atlas, begins with something that might sound simple but is actually one of the hardest tasks in astronomy, determining the exact path of an object moving through space. When astronomers calculate an orbit, they are essentially building a mathematical description of how gravity and other forces shape that object's motion over time. Even a tiny additional force can gradually shift the trajectory. When the object is millions of kilometers away and the force is incredibly small, detecting that shift becomes a delicate and complicated process. The official orbital solution used by the astronomical community comes from the Jet Propulsion Laboratory, part of NASA. The analysis was produced by navigation engineer Davide Farnochia, who has extensive experience calculating the paths of asteroids and comets. His solution relied on 782 carefully selected observations. That number may sound large, but it is actually a small fraction of the thousands of measurements submitted by observatories around the world. The reason is quality control. JPL applies strict filters to remove observations that do not meet precision standards. If a measurement appears slightly inconsistent with the others, or if the telescope calibration seems uncertain, that data point is excluded. The goal is to build a smaller but cleaner dataset that minimizes systematic errors. With this filtered dataset, the orbital model indicates that the radial acceleration, called A1, is about 5 times larger than the transverse component, A2. In simple terms, the comet appears to be pushed mainly away from the Sunday. That behavior fits perfectly within the standard understanding of comet physics. However, the analysis not remained completely unchanged. As scientists continued studying the object, new information about its composition emerged. Observations from the James Webb Space Telescope revealed that the coma surrounding 3I Atlas contains large amounts of carbon dioxide gas. That discovery matters because different ices sublimate differently as a comet moves through the solar system. Water ice, which drives activity in many comets, tends to release gas rapidly near the Sun and then decline sharply with distance. Carbon dioxide behaves differently. Its outgassing decreases more gradually as the comet moves away. To account for this, the orbital model was updated. The mathematical description of how the outgassing force depends on distance from the Sun was modified to reflect carbon dioxide sublimation rather than water ice. When that change was applied, the value of the radial acceleration A1 decreased significantly, though it still remained larger than the sideways component A2. According to this model, the comet's behavior remained consistent with ordinary solar heating driving the gas emissions. But another group of researchers approached the problem from a different angle. Instead of starting with a smaller filtered dataset, they decided to analyze nearly all the available observations. Their study was led by Federico Spada, working with comet dynamics expert Malgorzata Krolikowska and researcher Luke Dones. Their paper, posted in late February 2026, examined 7,788 astrometric measurements collected between May 2025 and February 2026. That is roughly 10 times more observations than the dataset used in the JPL solution. Instead of discarding large numbers of measurements, this team used a detailed statistical model to estimate the uncertainties associated with each observation. The idea was to keep as much information as possible while accounting mathematically for the varying quality of the data. This approach allowed them to test multiple physical models describing how the comet's outgassing might behave over time. Some of these models assumed symmetric activity, meaning the comet would release gas in a similar way before and after it passed closest to the Sun. Others included time delays, allowing the peak activity to occur slightly after perihelion due to thermal inertia inside the nucleus. The most interesting models introduced asymmetry, acknowledging that the comet appeared to fade faster after perihelion than it brightened beforehand. That pattern suggests that volatile materials near the surface may have been depleted during the close solar encounter. Across nearly all these models, two of the three acceleration components remained stable. The radial component A1 and the normal component A3 did not change dramatically when the assumptions were altered. The sideways component A2, however, behaved very differently. In many of the best-fitting models, especially those that incorporated asymmetric outgassing, the transverse acceleration was not small at all. Instead, it came out nearly equal to the radial push. This result has major implications. If A2 is comparable to A1, then the comet is not simply being pushed away from the Sun, it is also being pushed significantly along its orbital path. In other words, something about the pattern of gas escaping from the comet is producing a strong sideways force. The possibility attracted attention from several researchers studying interstellar objects, including Avi Loeb. In a public analysis discussing the new results, Loeb summarized the conclusion in straightforward terms. According to the new calculations, the comet appears to be pushed sideways almost as strongly as it is pushed outward from the Sun. That difference may sound subtle, but in orbital dynamics it can reveal important information about how gas is escaping from the surface. To understand why, we need to visualize the geometry of the forces involved. The radial component, A1, points directly away from the Sun. If sunlight is heating the sun-facing side of the comet and gas is escaping from that region, the reaction force pushes the nucleus outward along that line. That is the behavior expected for a typical comet. The transverse component, A2, points along the direction the comet is already moving in its orbit. A strong A2 implies that gas is escaping in directions that are not simply facing the Sun. For that to happen, the comet's rotation and surface structure must be arranged in a particular way. One possible explanation involves the orientation of the comet's spin axis. If the rotation pole is tilted relative to the Sun, certain regions may receive continuous sunlight while others move in, and out of illumination. Jets of gas emerging from those regions can produce forces that do not align perfectly with the Sun-comet direction. Another mechanism involves localized active regions. Comets rarely release gas evenly across their surfaces. Instead, activity often emerges from specific vents or fractures where volatile material is exposed. If one side of the comet contains more active vents than another, the resulting jets can create directional thrust. And this is where new observations from one of the most powerful telescopes ever launched begin to play a crucial role. High-resolution images from the Hubble Space Telescope revealed something remarkable about the structure of the gas jets surrounding 3I, Atlas. Instead of a random pattern of activity, astronomers identified several narrow streams of material emerging from the nucleus in a surprisingly organized arrangement. Those images, analyzed by Avi Loeb and Tony Scarampato, showed 3 small jets spaced evenly around the nucleus at angles of roughly 120 degrees. Even more intriguing, these jets appeared to wobble in a regular pattern with a period of about 7.1 hours. That oscillation matched the rotation period inferred from brightness variations in the comet's light curve. This pattern suggests that the jets are tied directly to the comet's rotation. As the nucleus spins, the active regions producing those jets sweep through space in predictable directions. The geometry of that motion may naturally produce the sideways push seen in the orbital data. But the story does not end there. The symmetrical arrangement of the jets, 3 of them separated almost perfectly by 120 degrees, raises new questions. Natural processes on comet surfaces can create active vents, but they do not usually produce such precise geometric spacing. That unusual symmetry has become one of the most intriguing features of 3I, Atlas. The strange pattern of jets seen on 3I, Atlas, is where the story becomes especially interesting, because those jets may hold the key to understanding the mysterious sideways push detected in the orbital data. When astronomers studied the high-resolution images captured by the Hubble Space Telescope, they applied a special image processing technique designed to reveal faint structures hidden within the comet's glowing coma. The surrounding cloud of gas and dust normally appears smooth and bright, which can hide narrow jets emerging from the nucleus. By rotating the image and subtracting the symmetric background, scientists can isolate the asymmetric features, streams of material, arcs of dust, and other structures tied directly to the comet's activity. When this method was applied to 3I, Atlas, the results revealed a very specific geometry. 3 smaller jets appeared around the nucleus, each separated from the others by roughly 120 degrees. Alongside these was a more prominent jet pointing roughly toward the Sunday. The 3 smaller jets did not remain fixed in the images. Instead, they oscillated back and forth with a regular rhythm. The period of this wobble was measured at about 7.1 hours, matching the rotation period inferred from brightness variations in the comet's light curve. This pattern strongly suggests that the jets originate from specific locations on the rotating surface of the nucleus. As the comet spins, those active regions sweep through space like rotating nozzles, directing streams of gas and dust outward. By tracking the changing positions of the jets over time, researchers were able to estimate the orientation of the comet's spin axis. Their calculations indicated that the rotation pole is tilted about 20 degrees away from the direction of the Sunday. That orientation is important because it changes how sunlight heats the comet's surface. If the spin axis pointed directly toward the Sun, the region near the pole would receive continuous illumination. But a tilt of 20 degrees means that the active regions near that pole are slightly offset from the direct Sun-comet line. When gas erupts from those locations, it does not travel straight away from the Sunday. Instead, the jets emerge at a slight angle. Now imagine 3 jets arranged evenly around the pole, each separated by about 1/3 of a full circle. As the nucleus rotates, each jet contributes its own tiny push to the comet. When you combine the forces from all 3 jets, the result is not perfectly radial. Instead, the geometry naturally produces a component of thrust pointing sideways relative to the Sunday. That sideways force corresponds exactly to the transverse acceleration scientists describe with the parameter A2. This is why the orbital analysis presented by Federico Spatada and his colleagues becomes so intriguing. Their calculations indicate that the transverse acceleration of 3I Atlas may be nearly as strong as the radial acceleration pushing it away from the Sun. The jet geometry seen in the Hubble images provides a physical explanation for how that could happen. Two independent lines of evidence, astrometric measurements of the orbit and direct imaging of the comet's jets, appear to point toward the same conclusion. In science, that kind of agreement between different methods is often a sign that researchers are on the right track. When one measurement explains another, confidence in the interpretation usually increases. The idea that the sideways push could be produced naturally by the comet's rotation and jet configuration is therefore considered a plausible explanation. Yet even within that natural explanation, there are details that remain puzzling. The most obvious one is the symmetry of the jets themselves. Active regions on comets typically appear where fractures, craters, or erosion expose buried ice. These features usually form in irregular patterns. There is no known geological process that would naturally arrange three vents around a nucleus at exactly equal angular intervals. The near-perfect 1, 2, 0 degree spacing observed in the jets of 3I Atlas is therefore unusual. Researchers describing this pattern have used a careful word to characterize it: enigmatic. The term does not imply anything artificial or supernatural. It simply means the observation does not yet have a clear explanation within the existing framework of comet physics. Sometimes nature produces structures that appear orderly even when they arise from chaotic processes. But until scientists understand the mechanism responsible, the symmetry remains an open question. This is not the only unusual aspect of the object. Chemical measurements suggest that its composition differs in several ways from the typical comets found in our own solar system. Observations indicate a high ratio of carbon dioxide relative to water, along with elevated levels of molecules such as methanol. None of these substances are impossible for a natural comet, but the combination of these chemical traits together with the unusual jet geometry and the strong sideways acceleration makes 3I Atlas one of the most unusual visitors ever detected. Because of these anomalies, some researchers have considered more speculative possibilities. One of the most widely discussed ideas was proposed by Avi Loeb, who suggested that scientists should not completely rule out the possibility that an interstellar object might be technological in origin. Loeb has emphasized that this suggestion is not a conclusion, but a hypothesis worth examining carefully. In science, extraordinary possibilities must always be evaluated against the evidence. For the propulsion idea to be correct, the object would need to generate a sustained sideways acceleration, similar in strength to the one measured in the orbital data. The force itself is extremely small, about 1 micrometer per second squared, but it would need to persist for months. The jets observed in the Hubble images would also have to represent something other than natural vents, possibly functioning like directional thrusters. However, the propulsion hypothesis faces several challenges. The comet shows clear signs of natural activity, including a visible coma, dust tail, and emissions of common cometary molecules. Observations conducted with the SETI Institute using the Green Bank telescope did not detect any radio signals or technological emissions associated with the object. While the absence of radio transmissions does not completely rule out advanced technology, it removes one of the simplest forms of evidence that might support such an idea. For now, most scientists consider the natural explanation, the combination of rotation, localized jets, and unusual geometry, to be the most likely scenario. But acknowledging that explanation does not mean every detail has been solved. Science often progresses by identifying the limits of what we understand. Fortunately, an important test of the competing orbital models is approaching. On the 16th of March 2026, 3I Atlas will pass near the giant planet Jupiter. The enormous gravitational field of Jupiter will slightly deflect the object's trajectory. Because astronomers can calculate that deflection with great precision, the flyby will provide new data that help refine the orbital models. If the predicted path matches the observations, scientists will gain confidence in the current explanation. If not, the discrepancy may reveal additional forces acting on the object. What we can say with certainty right now is surprisingly simple. 3I Atlas is not following a purely gravitational orbit. A small but measurable force is pushing it. The magnitude of that push is tiny, but its direction carries valuable information about the physical processes occurring on the object's surface. One analysis suggests the push is mostly away from the Sun, while another indicates that the sideways component may be just as strong. At the same time, telescopes have revealed a rotating pattern of jets that could naturally create such a sideways force. The symmetry of those jets remains unexplained, but it does not violate any known physical laws. As more data arrives, scientists will continue refining their models and testing their assumptions. For now, the honest conclusion is that 3I, Atlas remains one of the most fascinating interstellar objects ever discovered. It behaves in ways that are unusual but not impossible for a natural comet. The upcoming gravitational encounter with Jupiter will sharpen our understanding, but it may not answer every question. That is the nature of real scientific exploration. Each discovery reveals both answers and new mysteries waiting to be solved. If you enjoyed breaking down this cosmic puzzle and want to keep exploring the strange visitors entering our solar system, make sure to like the video, subscribe to the channel, and share your thoughts in the comments, because the next discovery might change everything we think we know about objects traveling between the stars.